Hi, welcome back. This is Professor Lemieux again, and for second conservation of mass screen capture, prepared for you a small applied problem. I went ahead and I wrote up the problem in the interest of saving some time. And what we're going to be doing here is we're going to be applying the conservation of mass in the form that corresponds to the Reynolds transport theorem number 2. So not the most restricted form. If you remember, the assumptions there were on the most restricted form was that the flow was uniform across every cross section, that there was only one inlet and outlet, and 3, that the velocity was exactly perpendicular to each of the openings, the two openings of the flow. In the form number 2, it's the same 3 restrictions, except that we remove the one inlet, one outlet, and we allow for multiple inlets and outlets. So only 2 of the restrictions are strictly kept in the formulation. All right, so here's the problem we've got. We've got a pipe. It's a pipe section shown right here. And this pipe section's got three regions where the flow can come in or go out. Region 1, I've labeled them already for us. Here's the flange, and we've got a unit vector pointing outwards. Section 2, here's the flange with a section of the pipe below it. Unit vector pointing outwards. Remember, unit vectors are always pointing away from the control volume. And section 3, here's the flange and the pipe outside of the flange and the unit vector pointing outward. Speaking of control volume, here's the outline of the control volume that we're going to be using for this problem, since we're interested in the flow inside the pipe junction itself. We're not really resolving for forces here in this problem. The game plan here is to just resolve for the flow through it. But in general, I'm going to ask you to do two control volume representation. One for free body diagrams and one for mass flow diagrams. Since we're doing continuities here, continuity exercise, we're going to be focusing on mass flow diagrams. So let's write that down. Mass flow diagram. MFD for short. Okay? Alright, so we've got this set up, this geometry as I've outlined to you right here, with a few more things that are given to us. We have steady flow in each of the water pipe junctions. So if you recall the form of our conservation of mass, that means that the unsteady term, the first term, is going to go to 0. That's kind of nice. And we're being given some other geometry data here. So to add that to our mass flow diagram here, I'm going to pick a different color here so that we can highlight the stuff that's given to us on the diagram. So the flange pipe cross-sectional area at the flange number 1 has an area of 0.2 square meters. So let's put that down. A1 is equal to 0.2 meter square, sorry. At area 2, the area is also 0.2 square meters. Whereas at section 3, there's some sort of a restriction going on there, and area 3 is equal to 0.15 square meters. Okay, so we're given all that. Hey, look at that. We're also told that there's a 4th section in this setup, 4th section at 4, that has a leak with an estimated flow rate of 0.1 cubic meters per second. So let's put that down. That's Q4. Q4, of course, is going to be equal to the product of A4, whatever that is, times V4, whatever that is, and the product of those two parameters at 4 is 0.1 meter cube per second. All right. Finally, we're told that the average speed at sections 1 and 3 respectively are 5 meters per second inward. All right, so let's put that in. Inwards at section 1, outward at section 3, not 2. Okay, and let's go back to putting the value for those. 12 meters per second at 3. And what is it, 1? 5 meters per second at 1. Okay, this is getting in my way. Oh, shoot. Let's see. Alright, there we go. Okay, V1 is equal to 5 meters per second. Okay, so we've got all the data that's given to us in a nice, clean mass flow diagram. And the question is, find the velocity of the flow at section 2. What is the flow coming out of section 2? Now, I don't know which direction it's going. I'm indicating that it's outward, and we're going to solve for it assuming that it's outward. What that means is, at the end of the day, if we end up with a negative number, we just know that our direction was wrong, and the flow is in fact inward. Okay. All right. So for a solution, let's start by solution by stating your assumptions. One, we're assuming that we have steady flow. That's a good one because it's given to us. Two, we're going to assume that we have incompressible flow. Meaning that rho of water is a constant. Pretty good assumption for a pipe junction. And three, even though it's not explicitly stated in the problem, we are going to assume that we have uniform flow properties at each section. Okay? And we're going to let V be our control volume, which is fixed in this problem. Okay? All right. So let's use the form of conservation of mass that corresponds to RTT number 2. And we have that the rate of change of mass of the system with respect to time by continuity, conservation of mass, we know that that's 0. And we know by RTT number 2 that that's the integral of the control volume of rho times the intensive property that corresponds to mass, which is just 1, times dV and ddt of that. Okay, minus sum over all the inlets of rho I VI AI plus the sum over all the outlets of rho J VJ AJ. Okay, and I should point out in my assumption here, a fourth assumption that I'm making is that V2 is positive outward. Alright, here's a good time to introduce my notation for positive here. I'm going to be using that throughout the course. That means positive, and you've guessed it, this means negative. Okay, so here I'm assuming that V2 is positive outward. So that means that that's going to count in terms of my summation for outlets. Okay, all right, so we know that the flow is steady. That means that that term here goes to 0, and we're left with sum over all the inlets of rho I VI AI is equal to sum over all the outlets of rho J VJ AJ. Looking at our mass flow diagram here, we have one inlet and 2 outlets. So one inlet, that's our left hand side, which is inlet number 1. All the densities are constant, equal to rho W, so we'll start with that. V1 A1, done for the inlets, is equal to all the outlets, which is rho W V2 A2 plus rho W V3 A3 plus rho W V4 A4. The leak, we're told, is outward, so therefore it's leaking outward like this. Okay, well, first of all, we notice that we've got the rows everywhere. Can knock them all off. They're all cancel out easily. And what are we given? We're given V1, V3, and V4, A4. Let's substitute for that. V1 is 5 meters per second. A1 is 0.2 meters per 0.2 meters squares. 1.5 meters per second. 0.2 meters square. Let me make sure I got that right. Oops, 5 meters per second. 5 meters per second, 0.2 meters squares. Okay, V2, that is equal to, we don't know, but A2 is 0.2. V2, 0.2 meters square, plus A3, V3, 0.15, and 12. Meters square, 0.15 meters square. And finally, V4A4, the product of V4A4 is given to us as 0.1 cubic meters per second. One equation, one unknown. Do not have my faithful calculator here, but I'm going to try and do this quickly. That's 1 meter cube per second is equal to 0.2 V2 plus 12 times 15. 5 times 1.8 meter cube per second plus 0.1 meter cube per second. That means that V2 is equal to 1.9 minus 0.9 meter cube per second divided by 0.2 meters square. 5 times should be 4.5, yes. Minus 4.5 meters per second. Notice the minus sign? That means that our assumption that the flow was inward was invalid. Sorry, outward was invalid. The flow is actually inward. So therefore, the flow at 2 is inward at 4.5 meters per second. Going back to our mass flow diagram, we could write that V2 is equal to 4.5 meters per second in that form. Problem solved. Okay, that's our problem. 15 minutes. Well, that's a good time frame for a problem here. Gives me plenty of ideas. Okay, good. That's our first problem. Hope you got something out of it. See you in class.